Hello everyone. Today I'll be doing a very low-level video on hypotheses and significance. So it's going to be very basic, and if you have quite a bit of experience with statistics, you will find little to nothing new in this. This video is mostly meant for people who are not quite as familiar with statistics as they would like. And I will be covering things like what is the null hypothesis and what alternative hypothesis if you have a research question, uh, what is significance exactly, and how do you draw conclusions and interpret results. So rule one of the null hypothesis is that it always includes equality, and that's usually only the equality. And that means basically that in the null hypothesis, whatever you're measuring is equal, or there's no change, or there's no difference, or there's no effect. So if you have a difference, it's usually not the null hypothesis. The alternative hypothesis does show the difference between things. So it always involves inequality, and there can actually be more than one. So there can be words in it like there is an effect, there's a difference, the two groups are not equal, or A is bigger, higher, smaller than B. In the last few cases, the alternative hypothesis has a direction, so it's bigger, not smaller, and it's smaller, not bigger. And in these cases, this is one exception to the rule of equality for the null hypothesis, of which there can only ever be one per research question. That's also something to note. And in these cases, for example, with a one-tailed test, the alternative hypothesis will be A is bigger / smaller than B, and the null hypothesis will be A is equal or smaller than B. So also, if you have two alternative hypotheses, one being one is bigger than B and the other being A is smaller than B, then you have bigger and smaller covered, and you will have one null hypothesis saying A is equal to B. So the null hypothesis covers whatever the alternative hypothesis doesn't, but it must always include equality. Then we go to significance. What you're actually doing with significance is looking, here we have a null model, so we expect a certain values in the population under the null hypothesis. And here we have the observed data, and the big question is the difference between the two so big that the measured data is unlikely to be part of the null model? So if I have two groups and there's a difference of 1 between them, is that 1 point difference big enough to be so extreme that it's unlikely that the two groups are the same? What is significant is very relative to lots of things. For example, 1 point on a test is very relevant. 1 year in age, not so much. So it depends on scale, and it also depends on something called power, which is the chance of finding an effect if there is one. And this is mostly moderated by things like sample size, with higher sample size increasing the power and thus making it more likely that you find an effect if there is one. And if you have a really high power, you get the thing called relevance. Is you have a significant effect, is the effect big enough to be relevant? Because people are not going to be eating seaweed every day for their whole life to increase their average life expectancy by like 3 months. For very low power, you have the opposite issue. So if you find an effect with this, it is very likely that the effect is big enough to matter, but you might not find this effect at all because you happen to have a data set that happens to be slightly closer to the null model than the observed data, than the actual population values, which are very different from the null model. Or you might even not find a significant value here, which would be strange. So what is significant is very relative, except that it's below a p-value below a certain number. So significance has this cutoff value for the p-value called the alpha, and anything under the p-value, that p-value is significant. By convention, the alpha is 0.05, but this is by convention. It's a rule of thumb, not a rule. So you can pick a lower alpha, and that will give you a higher probability that your null hypothesis is actually false if it's significant, and you're not just having a chance finding because the p-value, the data happen to be different from the null hypothesis because you happen to draw a small sample which happened to be extreme. And in that case, there is no difference, but you do find one. And a lower alpha decreases the chance that this problem occurs. So why don't we use a lower alpha? Well, alpha, the people tend to vary, so an alpha of 0.05 is already pretty hard to reach, but so a point below that. And if you could decrease it like to 0.01, you're also decreasing the chance that you find an effect if there is one. So lower alpha means less chance of finding an effect if there is none, but it leads to a lower power, which also means that you are less likely to find an effect if there is one. And that's why we use alpha 0.05, because we found that this is pretty okay and it leaves some power in your research without making the sample size really big to compensate. So now we know what the significance is, we know what the null hypothesis is and the alternative hypothesis. So how do you draw the conclusion on your data? Rule number 1 for this is, as you've noticed, we haven't mentioned the alternative hypothesis since talking about hypotheses, and that's because we usually only test the null hypothesis. So rule number 1, you cannot make any statements on the alternative hypothesis. So I accept the alternative hypothesis, I reject the alternative hypothesis, the alternative hypothesis is correct, it's just all wrong. Rule number 2 is that we test the difference between the null hypothesis and the observed data and check if it's big enough that the observed data is unlikely to come from the null model. We don't check if the observed data is close enough to the null hypothesis that it must be from the null model. As a result, we cannot accept the null hypothesis either. So we cannot make any statements on the alternative hypothesis, and we cannot accept the null hypothesis. So what can we do? And these are the words you will be seeing in most papers. That either the null hypothesis is rejected, so it is unlikely to be true because the difference between the observed data and the expected data was so different, or that it cannot be rejected because the difference between the observed data and the null data was not, so the expected value of the data was not big enough. So how do you interpret it? You now have a p-value, you have either accepted or you have not accepted, you have either rejected or not rejected the null hypothesis. So what does that say? Well, people sometimes make the mistake of thinking that a p of below 0.05, so a significant effect, is always positive, but it is not. Usually it's true. Usually you want an effect. So if you have developed a new medication, you want it to be better than the old one, or you want it to improve the condition of patients. If you have a new studying technique, you want kids to have higher marks when using it, or should study a shorter time. But there's also occasions where you don't want a difference. And the most common one that you will see for this is assumption checks. Because what you're doing with assumption checks is saying, what you're doing with assumption checks is saying data, for example, Levine's test. Data, are the two groups do they have equal variances? Because I need equal variances for my statistic tests to work. And in that case, equal variances already says it is equal, so it's the null hypothesis. So in that case, you want the null hypothesis to be true. Well, we cannot check that. We cannot accept the null hypothesis. We can check if it's so different from the null hypothesis that we can't say that variances are equal. In this case, so p below 0.05 is a negative thing and something you want to avoid. And you would have to alter your data by transforming it, for example, to fix it. There is possibly sometimes you might want to do the same for research, but this is very rare. But an example of this would be that you have a cheaper treatment option and you want to prove that it's not significantly worse than the more expensive one. And thus people can use the cheaper treatment option. And at times it doesn't really matter. It's mostly the case if the power is high enough, because if you have like 20% chance of finding an effect given that there is one, if you don't find an effect, it's probably by chance. Or it might not be, you just don't know. And but if the power is high, it's weird that you don't find an effect. So at least you know that there is unlikely to be an effect. And in these cases, no effect means as much as some effect. And for new treatment options, that's pretty shitty because it means that your new treatment option doesn't work. But if you're doing like observing things like do ethnic minorities get paid less than ethnic majorities? If you find that it is not the case, so if you can't find a difference between ethnic minorities and the ethnic majority in salary, then it doesn't really matter what you find, because if there's no difference, it's cool. If there is a difference, that's also something that you might want to do something about, because that's another type of inequality. I hope this helps with understanding and interpreting results. If you have any questions, please do ask, because understanding at least most of this video means that you can do statistics properly, at least on the basic level. Thank you very much for listening.